tell you a little bit about today is to give you a brief, hopefully brief overview of some research that was funded by the Cultural Center in Oman, specifically looking at vegetation dynamics and impact of grazing in the Dhofar Mountains near Salalah. And this is work that was done, it was actually initially inspired by a report that Andrew Spalton at the report in Oman had done, urging a study of the impact on vegetation, the endemic vegetation in Dhofar. And so we took some of the tools that, some of the satellite-based tools that we use, that we've developed in other parts of the world, and try to apply them in Oman to try and understand what is the impact of grazing in the mountains. And so I'll start out saying a little bit about Dhofar and the landscape there, and show you some of the on-the-ground observations that we made of the direct impact of cattle and camel and to some degree goat grazing. And then I'll show you some of the analysis, the results of the analysis that we did using different types of satellites to try and map the changes with the satellites. And then I will end with a much more detailed view from a newer type of satellite. And even though the title may imply bad news, I think the end result is good news for Dhofar. So I'm going to try to I'll try to be as non-technical as possible. If I say anything, if I slip up and use jargon and you don't understand what I said, please stop me and ask me to explain, because if you don't understand, probably nobody else does either. So what you're looking at here is an elevation map of the southwest corner of the Arabian Peninsula, where it's being ripped out of the African continent. And so the seafloor spreading that's been going on for the past several million years in the Red Sea and the Gulf of Aden is a result of the Arabian Peninsula, Arabian Plate's movement to the northeast. And so when you rip a continent apart, or when a continent gets ripped apart, a lot of things happen. It's pretty dramatic. The process of ripping causes hot mantle from deeper in the earth to come up. It causes a lot of melting, causes a lot of volcanism. It also causes the area that's being stretched to thin and swell, or thin and rise as it's hotter. And so on the edges of rifts, you see very typically what you see here on the southern corner of the Arabian Peninsula. Use the mouse to do this. You see these uplifted rift flanks. These are very common. You see the same thing between parts of West Africa and Brazil, where they ripped apart. And so the terrain in Dhofar, where we're looking, is the easternmost extent of that rift impact of the uplift from the rifting as Arabia is being pulled out of Africa. And so we'll be looking in the Dhofar Mountains, specifically this area right here. And a little closer view. This, for those who are familiar with the geography of Oman, this is the area right around Salalah. And if you know about the geography of Oman and Salalah in particular, you probably know that it's famous for the khareef, the monsoon. The terrain here catches a little bit of the southwest monsoon and causes the uplifted terrain causes the moist air to move up, and as it moves up, it rains. And so you get, in an otherwise very dry place, you get this very localized, persistent mist and rain that occurs in the summer every year. And so what are referred to as the Dhofar Mountains are this area here, which is not a typical mountain range because it's really kind of a ramp. It's uplifted on one edge and then drops off very, very gradually as you go up into the Nedge and the Rubicala to the north. But because the escarpment is so steep, the moist air goes up rather quickly, and so when that happens, the water vapor in the air precipitates out in the form of rain. And so the effect is what you see here. These are satellite images that I'll explain in more detail in just a moment. This is what the area looks like before the monsoon starts, before the khareef starts. And this is what it looks like. This image in the center is what it looks like for about 2 months, 2 to 3 months every year, as the moist air forms clouds that just hang over top of the range. Or the two ranges really, the Jabal al-Khara and Jabal al-Qamar here. And you can see what the result is in usually September when the clouds clear. The result is that the mountains are completely covered with very lush vegetation. There's a couple of photographs here from Andrew Spalding, who's been working in this area for quite some time. And you see it's very lush. It looks like a sky. And not long after that, though, the clouds clear and the water starts evaporating, and the plants start transpiring in the water, and basically the area starts to dry out. And so it doesn't stay green for very long. It's very green, and then it desiccates really quickly until next year rainfall comes. So what I'm going to show you now are a series of other photographs, field photographs from these different ranges to show you some of the range of landscapes that we have here. We'll start in the east, the Jabal Samhan. This is as we drove in from Muscat. So we'll go from east to west. And the photos that I'm going to show you were not taken during the khareef. They were taken in sort of the January-March window when we were there doing field work. So this is what the top of the Samhan looks like as you're coming in from the east. And on this day, this particular day, there was a cloud deck set up, and so we're basically above the clouds here. And this is what it looks like after the clouds clear when you're down on the coast, looking back up at it. So what you're seeing here, this uplifted rift flank that used to be part of Africa. And that's about 1,200 meters relief on that big cliff face there. And this is what it looks like up on top as you start to go westward from the Jabal Samhan down into the Jabal al-Khara. And so you can see it again over on the coast in the distance. There's a lot of cloud, but here we're back beyond the point where the clouds come. And so what we have here is kind of a open woodland savanna kind of environment with seasonal grasses and trees that are somewhat green all year round. And as we go a little further east into the Jabal al-Khara, this is the largest and deepest of the wadi systems. The Jabal al-Khara has much more subdued terrain than the Jabal Samhan does, but this big wadi system that we're looking at here is the most deeply incised and steepest. And so what you can see on the sides of the wadis here is a forest. And then you can't really see it here, but what you can see is that the forest thins out as you start to get up into the more gentle slopes up on the top side.
Non-technical, could you explain what a wadi is?
Oh, sorry, canyon. Yeah, so it's a canyon. There's a network of canyons that you'll see in more detail in just a moment. And so a more typical terrain is shown here. This is my graduate student, Dan Souza, taking a photograph looking from the top of the Jabal al-Khara down onto the Sabala plain. And so that's the part of the city of Sabala there on the coast. And so this more gentle foothill kind of terrain is rented. And again, you can see it's a combination of this time of year, not much grass left, most of these trees, and kind of not quite forest until you come to the bottom of the canyon. And here's Andrew Spalding taking a photograph on a little bit steeper edge of a canyon. And you can see it's a bit more densely forested here. But what you can see on top is a transition to the range top grasslands. Many fewer trees and much less topography. And this is a more typical of a smaller upland end of a smaller body system. So this is all forest down here, and this is the transition to the range top grasslands there. And these plants here, the green ones, are known as Sodom's apple. I don't remember the Latin name, but they're generally considered an indicator of overgrazing and degraded landscapes. They're found all over the world where there's overgrazing, so that's one of the things people look for. And so now going further to the east into the Jabal al-Qamar, it's a much narrower mountain range, but much steeper, much more extreme terrain topography. This is about halfway up to the range top, looking back to the east towards Salalah. Salalah is just a little beyond the edge of the photograph here. And this is looking upward from there, and so you can see it continues up steeply until you get to the top of here. And once you're up top, it flattens out again. You have these range top grasslands that occur up there. And again, the sides have varying degrees, varying density of forest. And here's another shot. And here's an example of a transition from a full dense forest to a pretty open grassland. And here we meet the characters, actors on the stage. It's a small herd of Dhofari cattle working away at trying to get something to eat. There's a close-up. They're not the friendliest cattle. My grandfather was a cattle rancher, and so I've spent some time around cattle, and the cattle in Dhofar are not, I don't think they're used to having people wandering around in their territory. And so you can see this was taken in February of 2016. And you can see the grass is pretty much parched, but it still has some nutritional value. They still graze on it. These green plants here are plants that no animal will eat. They have, I forget the name of the plant, but they have something in the leaves that no grazing animal will touch. So those plants do just fine. And here are the other characters. It's a mob of camels next to an exclosure. I'll explain the exclosures later. The exclosures were a totally unexpected, very fortunate accident that we came across that really helped us out. I'll talk about that in a few minutes. And so you may notice on the side where the camels are, there's not a bit of biomass to be had. And right on the other side of the fence, there's plenty of it, and that's why the camels are at the edge of the fence. The camels are hungry. Now, apparently, neither the camels nor the cattle get enough to eat, enough nutrition later in the year. At this point in the year, when most of the grass has been senesced or eaten, they have to be fed food supplements. And so they go out and they pretend like they're grazing all day long, and then they come back home at night and get fed Snickers bars or the cow equivalent of Snickers bars. Okay, wrong direction. Okay, and then there's none of these are not wild camels. When I first saw the photos, I thought they might be wild. Apparently there's not one wild camel in Oman. They're all owned by somebody. And here's one of the tenders taking them out to kill a tree. Actually, they're almost at the limit of what they can get from that tree. A lot of the trees, bigger trees like this, have enough out of reach of the camels. They do okay. It's the trees in the Anagaisis forest and the canyons are not as tall, and they're more vulnerable to camels. And then there are goats involved as well. Goats eat anything. They can climb, they can fly. No stopping goats. And they're everywhere. They're on the roads. They're in parking lots. They're all over the place. And so here you can see some cattle grazing on hill slope, and you can see that they're kind of making these little, it's almost like a terrace effect. And this is a very easy way to tell when you have a lot of cattle, because they walk along the same trails. And so you can see this entire valley, this entire canyon network here has been grazed down to the ground. And you notice also around the bushes in some places where the grazing pressure is really heavy, you see these halos of brighter soil, exposed soil, where all every last bit of biomass has been scraped away. I think that's from them standing there and trying to eat the bush, and it's their feet that are grinding the soil away there and making it brighter. But yeah, in areas where you see that, there are some really hungry animals.
If the biomass so if that wasn't so heavily grazed, would the biomass on the flat land be just as heavy as it is on the slopes?
No, in terms of biomass, there wouldn't be, because the slopes have full-on forest. And so the trees are more densely packed, they're closer together, and there's more what's called understory underneath the trees when it's green, and so there's absolutely more biomass on the slopes. But right after the khareef, when everything's green, there's the range tops look like a tall grass meadow that you can see anyways. There's a considerable amount, but it's hard to beat trees for biomass. They have a big advantage. And so these are all examples of things that we can see in the field where we can document. This is an area that's heavily grazed. You get an idea of how heavily grazed it is by how much of these impacts you see. This is an interesting area. This is on one of the high cliffs between the Jabal al-Qamar and Jabal al-Kara, just to the west of Salalah. And this is what's called a stack. And this is a big column of rock that's separated from the cliff. And according to my GPS, the altitude up here is 224 meters down to sea level. And so this thing somehow separated, but as you can see, there's grass growing over here. And the grass on this side, it's eaten right down to the dirt. On this side, you've got probably waist high. The grass is senesced, but it's still there. And so, because no animals can get there. So that's an indication of what this whole area would look like if it weren't for the grazing. Okay, so that's what the landscape looks like now. A little bit of science. So we use satellites to try and map to try and quantify rigorously the way that the land surface is changing. And effectively, what we like to... Do you want me to stop for a second? What we like to do is basically make a series of vegetation maps. At the very least, we'd like to see where there's vegetation, how much vegetation there is, how dense the vegetation is in different parts of the landscape. What we'd really like to be able to see is what type of vegetation it is, and not just trees versus grass, but one of the holy grails is to be able to map different species of trees or different species of agriculture. And we're not quite there yet, but we do have a lot of experience. We, the community of people who use this kind of urban sensing, has a lot of experience mapping vegetation. And for a reason I'll explain in just one second. So the instruments we use are basically just like digital cameras, very sophisticated digital cameras onboard satellites in orbit. The main difference is that a normal digital camera images three colors. It images red, green, and blue brightness, and then it sandwiches those three primary color brightness images together to make an image that looks like what our eyes detect. The instruments that we use also image in the infrared beyond the range where our eyes are sensitive. And what we really like to measure is a quantity called the reflectance. And reflectance is a physical quantity, it's a physical characteristic of everything that reflects light that determines what we perceive as color. And so our eyes are actually very complicated. Our eye-brain system is a very complicated sensor. These electronic sensors are much simpler. And so we take an instrument into the field with us called a handheld spectrometer, and it measures the reflectance. It measures the fraction of the sunlight that's reflected off the surface of whatever you pointed at very narrow wavelength intervals over both the visible part of the spectrum and the infrared. And that's what these thick continuous curves that you see here are. These are reflectance curves that we measured in the field. And for instance, we'll start with a simple one. This blue curve here is a cloud. And clouds, we see clouds as white because they reflect visible colors in about equal proportions. And hence that's why you see this curve is fairly flat. It's reflecting all visible and the near-infrared wavelengths equally. Just as a point of reference, the wavelength units here are micrometers, so they're millionths of a meter, very short wavelengths. The visible part of the spectrum that our eyes are sensitive to goes between 0.4 and 0.7 meters. Blue is around 0.4, red is at 0.7, and beyond 0.7 is near-infrared. And so you can see that clouds are white, both in the visible and the infrared. Soil, this is why soil appears shades of brown, because it's less reflective in the blue and it's more reflective in the red. And it looks more like brown in our eyes. It's even more reflective in the near-infrared. Non-photosynthetic vegetation is basically like dry, dead grass, branches, dead leaves, things like that. And it starts to look more like soil. The longer it sits there, eventually it becomes soil. And finally, last but not least, this is what live, healthy vegetation looks like. It's really absorptive in the visible blue and the visible red, a little bit less in the visible green. And the reason for that is because it has two types of chlorophyll that absorb energy at those wavelengths and use it to power the plant's photosynthesis process. And so we see plants as green because they're just a little bit less absorptive in visible green than they are in red and blue. But the main thing is they're really absorptive. Vegetation is dark in the visible. But what happens is as soon as you get to the wavelength where our eyes cut out, it becomes really, really bright. And this is called a red edge. It's where it goes from being very absorptive to very reflective. And this is what distinguishes live, healthy vegetation from everything else. Nothing else has this feature, this characteristic shape. So the shapes of these curves are kind of like the fingerprints that we try and use to distinguish one type of land cover from another. Now what you see superimposed here, these dashed curves are showing the range of wavelengths where the satellite sensor is making its measurements. We don't yet have satellite sensors that can, well, it's not exactly true. The satellite sensors we have access to can't measure these continuous curves yet, although we're probably 3 years away from having that. The ones that we use are more like digital cameras in that they just measure a specific range of wavelengths. And so what you're looking at here are the sensitivity ranges of the MODIS sensor. That's what collected this image here, the ones in the previous slide. And so instead of getting this nice continuous curve with all this detail in it, we just get discrete measurements at these points. And so we have to infer from that. So the thing to notice here, the thing that we're using, that we'll be using in the rest of the talk, is we use a measure of the slope between the visible red and near infrared. Because notice that nothing has as steep a slope between this point and this point as the vegetation does. And so we have an index that's basically the difference between those two reflectances. And so the greater the slope, the more likely that the material is vegetation. And you notice the vegetation has the greatest slope. The dead vegetation, the non-photosynthetic vegetation, has a much lower slope. Soil has a lower slope still. These are the example values here. And then the cloud has basically no slope. It's flat. And so we're going to use the spectral slope to map what's on the ground. So here's a map. It's actually, this is the average of that index value over the course of a whole year. of the area. And what you can see is it really effectively identifies the vegetated areas of the mountain ranges and the coastal plain. The brighter the green up to white, the denser the vegetation is. And so, and these are just some field photos showing for contrast what we were just looking at. And so, especially in an arid environment like this, where you tend to either have a lot of vegetation or very little or none at all, it's a really, really effective tool. And so, the MODIS sensor, the MODIS satellite that we're using, images almost every place on Earth, almost every day. And so what we get when we take this index and make for every day we have an observation, an image, we make a vegetation map out of it, basically. And so what we end up with is a big stack of these vegetation maps.
You can turn it into a movie.
Yeah, in fact, you could animate this. I thought about doing that, but I figured that's just asking for trouble. It's tempting fate. But you can see in this kind of cutaway view, this is the area that in that red box there. So it's designed to slice through some different types of environment. These are the farms down in the Slawa Plain. And you can see the areas, well, you can see first of all in time, this is the calendar year. And so for most of the year, it's fairly dark gray. It's not a lot of vegetation. Then it's black because it's completely covered with clouds during the khareef, during the monsoon. And then here you can see when the clouds clear, everything is green, right? The lighter the shade of gray here, the more vegetation there is. And so everything is, it's like those photos that I showed you, the Andrews photos that I showed in the very beginning. Everything's super green. But then you see what happens is the areas where it's cutting through forest and the canyons stays green throughout the year. And the areas where it's on the grassland, it drops off very quickly. And so if you take one pixel, for instance, this pixel right here in that blue spot, and you look at just the time series of this index value, this vegetation index value over the course of the year, it starts out fairly low and it's getting, it's dropping a little bit through the calendar year, and then the monsoon starts and the clouds roll in. And so then it's nothing, right? Just remember the cloud values are flat. And so you don't see, it just sees the tops of the clouds, and then all of a sudden quickly the clouds clear out and the greenness has gone way up because of all the precipitation. But because grass doesn't have deep roots and it transpires water very quickly, grass doesn't last very long without water. You probably have noticed this here in the summer, we have a drought, right? You can almost watch your grass, your lawn getting darker. Whereas the trees can hang on longer because they have tap roots, they go deeper into the soil where there's more water. And so the greenness of the range top grasslands drops off really quickly after the clouds clear. Whereas the forest greenness drops off much more slowly over the course of the whole year. And so we can use the temporal signature in addition to the spectral signature to distinguish different types of vegetation. And to distinguish how they're responding, because different parts of the range get different amounts of precipitation depending on how the clouds set up. And so different years, different parts of the ranges have different progressions, different evolutions after the clouds clear. And so that can tell us, we can use the vegetation to tell us something about how much precipitation was happening in and under the clouds when we couldn't see what was happening. So, if you're not used to looking at plots like this, or if you just don't like plots like this, just ignore it, it'll be over soon. But this is for those who absolutely must know all the details. Here they are. What you're looking at here on the right column first is a gray shaded image. This is what we call a calendar plot, and it goes through the course of the year from January through December, left to right, horizontally, and go by year from 2000 to 2016 from top to bottom. And so what you see here, for every day of those 16 years, the shade of the gray indicates how green a particular area was. Okay, these are averages over a patch of pixels. And so the top row here are the range tops in the western part of the Jumbo Al-Khara. And what you can see here, for each year, you can see, kind of like the previous slide, fairly dark gray, low vegetation, then black as the clouds come in, then the clouds clear out and it's white, and then the white fades back to gray. Okay, and so for three different, the east, central, and west range tops, you see somewhat different patterns depending on how long the clouds are hanging over one part of the range or another, and how much water precipitated out into the soil. And so we wanted to see if there's any trend. Is this area getting progressively drier? Is it being deforested? Is anything happening progressively here? Yes?
The third row down, it looks like an outlier. What happened there in each of the squares?
Third row, which one, where?
In each of them, the third row down.
Oh, here.
Yep.
Yeah, okay, a couple of the years, there was problems with satellite, where every third image or so was just noisy. We don't know why, we weren't able to fix it. In a lot of the measurements, we excluded those years. There were 3 years where this happened. And yeah, you're right, that's very, very sharp eye. That was one, you can see the others here as well. Yeah, so those are outliers. We didn't include those in here. But so what we want to see is there a progressive change, right? On a certain day of the year, is the vegetation decreasing on that day of the year from one year to the next? And so the way we did that was we took a vertical column through here. We took 3 particular Julian days, 3 days of each year, and then for each of the 16 years, we took that average amount of vegetation and looked at how the average vegetation within each of these parts of the range tops changed over those 16 years. And so if there was something progressive happening, you'd expect to see the points either increasing or decreasing or something. And what you can see here clearly is that the variability from year to year in all of these areas, variability from year to year completely swamps any trend that might be present. And if you don't trust your eyes, if you trust statistics more than you trust your eyes, we have the regression statistics here on top. The S value is the slope, the estimated slope, and the P value is the confidence value. And basically the only of these cases where the estimate was statistically significant were the ones that had basically zero slope. And you can see why, right? I mean, it's hard to convince, I find it hard to convince myself that there's any real pattern in any of these. Except that the year-to-year variability is so great that it masks any trend that might be present. So that's the story with the range tops. Here's the same thing for different sets of the wadis in both mountain ranges. Same situation with the forests and the canyons. The year-to-year variability is so great that it masks any progressive trend that might be there. So, if you were expecting to hear that, Dhofar is being deforested and that there's going to be no forest left in 5 years and that the camels are going to take over, we don't see any evidence for that in these days. Now, there's a limitation, though, is that this sensor, the MODIS sensor, the reason that we can have coverage almost every day is because the pixels are large. And so it covers a very wide area, but the price you pay is you don't get a lot of spatial detail. And so we get a lot of temporal detail, but not spatial. So to complement that, we look at another series of satellites called the Landsat series. Landsat only revisits every place on Earth every 16 days, once every 16 days, as opposed to almost every day. But its pixels are not 250 by 250 meters like MODIS, they're 30 by 30 meters. And so we can see much finer scale features on the landscape with Landsat. And so what you're looking at here on the left is basically the equivalent of an infrared photograph from Landsat. Again, the green, the brighter the green, the denser the vegetation. And you're looking at a bit of the central Jebel al-Khara here. The canyons, the forested canyons are the bright green areas here. This is in, I think, October, Julian Day 85, 2015. And so it's not right after the monsoon when everything is green. We wanted to look a little bit later when the difference from year to year becomes more apparent. And so you can see the range tops are starting to turn brown. And then out here in the edge, it's that light color, so there's almost no vegetation out there. And then down here on the Salala Plain, you can see variations as well. And so the brown areas are areas that were probably covered with grass in September and have since started to senesce. And the green areas are still fully leafed out forest. So we use a process kind of like what I explained earlier to estimate how much within each 30 by 30 meter pixel, how much of that pixel is vegetation, how much is soil, how much is shadow. And that tells us something about the composition of each pixel. And so in these maps that you're about to see, the red channel of the image corresponds to the soil, the green corresponds to vegetation, and the blue corresponds to the shadow. So up here it's almost all exposed soil, almost no vegetation. Here it's darker, so it's like this purple shade, and that's because there's more dead senesced vegetation up in here. It makes it darker. It also casts some shadows. And then, of course, in the canyons, it's bright green. And so the difference between this and this is this allows us to use a unit that's easy to understand. It's just how much of the area of the pixel is covered with each of these different materials and shadow. So this is what it looked like in 2015. Now compare that to 2016. Now, the satellite is very well intercalibrated, so we can compare quantitatively one year to the next. And you can see the difference. The 2016 khareef was much stronger. It dropped a lot more precipitation, we think. The Jabalis, the Dhafaris who live there also told us this when we were out in the field talking to them. They said that the khareef that year was much better than the one year before. And so the satellite sees everything as greener. So what we're going to do now, I'll just show you a comparison of those 2 years, again from this Landsat satellite, with higher spatial resolution. And I'll show you some time series of greenness, vegetation, for different types of environments. So we have a foothill on the coastal side of the range. We have a canyon on the coastal side of the range. We have a range-top grassland on the coastal side. We have a canyon back further toward the desert. We have a range-top further toward the desert. And then we have an example here in which the very edge before you go into the edge. And so in each case, the 2016 greenness is in green and 2015 in red. And so, for instance, the range tops, both inland and coastal, are much greener in 2016 than 2015. Both of them drop off. The greenness drops off really quickly in both cases. But it stays greener in 2016. There was more precipitation, more moisture in the soil, and presumably more denser grasses and vegetation. The forests and the canyons, different story. They do, again, 2016 does start out as green or in some cases, or greener. Then it drops off a bit in the beginning, and then it just goes more slowly. And even in a dry year, the same thing happens, but there's noticeably more vegetation, certainly due to more moisture in the soil in 2016. And then once you get in back toward the desert side of the range, it never gets as much precipitation. And then, so it's never very green. And on the coastal side, the range front the coastal side, look at that, the forest, the 2016, it just goes really slowly. 2015 drops off much faster. And so this is another illustration of the effect of 1 year's precipitation compared to another's on vegetation throughout the whole rest of the year. And finally, the last thing I want to show you here are the effects of some what are called exclosures. They're basically fenced-in areas that the Ministry of Agriculture and the Ministry of Environment build and to varying degrees maintain. And so they're basically chain link fenced-in areas in different parts of the range. And so if the fences remain intact, it keeps the animals out. And so this gives us kind of a natural laboratory to look at what would happen if animals can't get in and graze versus where they can. And so what you see here, in white are our driving tracks. We drove, I forgot how many thousands of kilometers we drove while we were there. We were there for 6 weeks times 2 years. And yeah, we drove a lot. I think something like 18,000 field photographs. And you only had to look at 20 of them. And so the exclosures, you can see the exclosures here. They're labeled according to their code numbers. And you should actually be able to see the effect of the exclosure because you can see our GPS track, the white track going around the edge of the explosion. And you can see, in most cases, inside the polygon, it's darker. And the reason for that is because the grass is longer. You know why the grass is longer. Longer grass casts more shadow, and so it appears darker. And so we wanted to compare the inside versus the outside of the exclosures. And so the exclosures, most of them were big enough that we can use the Landsat imagery. The pixels are small enough that we can actually take an average of pixel greenness time series inside an exclosure and then in surrounding areas outside. And okay, so that's 2015, 16, on almost the same Julian day, only 3 days different. 3 days different, Julian day 278 versus 281, so effectively the same day of the year. And look at how much greener it is in 2016, 15. These are clouds down here. So if we look at the inside versus the outside of the exclosure, inside green, outside red, and 2015 across the top, 2016 across the bottom, initially you can see the difference. Definitely greener, more vegetation inside than outside. And in some cases, in this exclosure, it stayed greener on the inside throughout most of the year until everything was dried up. In this one, they both kind of dried up eventually. Here, same thing. Eventually, they come together. And so this shows us both at the very end of the monsoon and then throughout the year how much of a difference that fence makes. So the difference between the red curve and the green curve is crazy. Because otherwise there's no difference. Except for one thing, you might wonder, well, why would it be greener inside the fence right after shouldn't they get the same amount of rain? Shouldn't they start at the same greenness and then separate as the grazing goes on? The reason for that is the standing grass, the standing vegetation, which you'll see a photograph in a second. The standing vegetation, when the cloud, the mists blow over the landscape, as soon as the mists touch something, water vapor, water droplets condense on it. And so standing grass basically acts as a capture device for water. This is how they do fog harvesting. They hang nets, and the fog will condense onto the net and run down the net. And so the grass is basically acting as a fog harvester here and drawing more water out of the atmosphere into the soil. In fact, in some areas where the grass isn't as tall, we see a fence effect where the water condensing onto the fences runs down, and you see tall grass right on the inside of the fence, but not further in from the fence. Yeah.
Why would it be on the inside lower than on the outside? You have several grass spread.
Oh, when it gets down really low in the end?
Yep.
Yeah, that's...
And the one above, and the one there, yes, the other.
You know, when it gets down below about 10%,
You can't measure it.
you know, then things like atmospheric effects later in the year and dust and aerosol scattering start to impact the
But
measure.
that's strange.
It is strange. Yeah, I agree. I blame atmospheric effects when I don't have a good answer. So I don't know why that is, but yeah, I agree. It's odd. But the lower the value, the less trust we have in it.
Do you have an opportunity to visit this fog harvesting project?
Do we have
Still going on, the fog harvesting?
So they did have nets in some of these exclosures. It looked like they were doing some kind of fog harvesting, but it looks like none of these exclosures are maintained. I'll show you photographs of them in just a second. But yeah, there was a research scientist, Anke Hildebrand, who did some really interesting work on this effect. She called it horizontal precipitation back in the 1990s, I think it was. And did field experiments and things and documented that this happens. And so we're kind of inferring that's what's happening here. So now to close, I'll just show you, well, actually I'll show you, I have one more set of images to show you before. But these are just photographs of some of these exclosures, and I don't have to tell you which side is the inside and which side is the outside. You can see the difference in the amount of grass there is on the ground. This is what happens when the camels can get their necks over the fence and start to pull it down. But you can see from the amount of grass on the inside, they didn't get completely in. They pulled it down. They weren't completely successful. Some cases, they pulled the thing down entirely, or maybe their herders do it for them. And so some of these have been compromised. And all it takes is one hole, and then, game over. This is looking through the fence, and so the foreground is inside. This is one of the ones that's further back in the range, and so it starts out drier. But you can see there's this silvery senesced grass inside, and then as soon as you cross the fence to the outside, it's just bare dirt. And this is the same effect, but in a case where someone just built a stone wall. The stone wall is like waist high, so it's apparently high enough to keep the camels out of the cattle. And so here you can see a big difference in the amount of grass that we have. Okay, so you might imagine the logical thing to do would be to take these vegetation maps from the same time of the year, like what I was showing you, the flipping back and forth before, and just subtract them. Maybe we could use that as a way of identifying places where there have been big changes. And so that's what we did here. We took the vegetation maps from the Landsat, and we subtracted one from 1987 from the one in 2016. And so any place you see a lighter shade of gray, that suggests that vegetation increased between 2016 and 1987. 1987, I think, was a wetter year, and so it should be comparable to 2016. And so lighter shades of gray suggest increases in the amount of vegetation. Darker areas suggest decreases. And what you see, in contrast to the bad news scenario, is that I see a lot more lighter gray than darker gray, which suggests to me that at least between these 2 years, it increased.
What's the baseline grade?
The baseline is no change.
But what's the baseline in the picture? You're saying the lighter gray and the darker gray, and there has to be a baseline.
Oh, sorry, 20%. The maximum, the whitest area is a 20% increase in vegetation, fractional vegetation, and the black area is 20% decrease. And so there are big things like this. I don't know what was developed. I guess there must have been a farm here in some of these areas. These are cloud shadows. And now but then we did the same thing for 2015 versus 16, and you see big changes there too. And so that's just seasonal. That's not that much land cover change in 1 year. So that's seasonal, and this is some amount of seasonal and some amount of real land cover change. Wrong direction. Okay, now finally, the last bit. We have, if you spend any time looking at Google Earth, you may wonder, well, why are you using 30-meter imagery? Why don't you just use the high-resolution imagery like what you see in Google Earth? And we do, but the reason is you don't get complete coverage with that kind of high-resolution commercial imagery. I mean, in cities you might, but here in Dhofar you don't. And so we were lucky to find four scenes from 2002, 2003, 2016, 2017 that had some overlap, so we could look at some areas between those years, so basically 15 years separation. And so now I'll show you at higher resolution, to the point where you can see individual trees, some of the changes that have occurred. So of course there's been development, people are building and expanding their homesteads. And so here's March 2002, February 2017. You can see a big paved road came in. The brighter dirt roads disused, and so they're not as bright. You can see new homesteads, of course, individual trees, but what's interesting is you can see individual trees getting larger as they grow over the course of 15 years. You can see canopies of individual trees expanding as the tree grows. I can see an example here. And of course, in some cases, they're smaller. This area here and here, they planted trees. But if you look over in the edge of the canyon here, you can see it's more closed out. You can see more spaces between the trees in 2002 than in 2017. Similarly, in another canyon, 2002, 2017, what happened here, this must have been a flood, must have been a flash flood, came down the wadi and washed all those trees out. There must have been a big, in fact, we know from the 2003 image that it happened between 2002 and 2003. And here another canyon, and another wadi open area is larger. The camel herders will take their camels up into the canyons to browse, but camels don't tear down trees like that. This must have been, because it's in a drainage, it must have been a flash flood that came through and cleared it, and then made it easier for the camels. And so I think I've said everything on here already, so I won't bother. But sorry for going longer than expected. Thank you for your attention.